Hello everyone. In this series of lectures, we'll be solving some problems from the design. So, in this topic, we'll be solving a simple problem from the concept of combined loading and principal stresses. Here, I will not be explaining the theory in detail, but the same will be discussed while solving the problems. So, here a circular shaft is given, its diameter is given, which is fixed at one end and it is subjected to two types of loading. One is axial load and a torque. That loads are shown here, values are given. The length of the shaft is also given. Here we have to determine the combined effect of these loadings, that is the principal stresses at the most critical point. Critical point means the point or the location within this member where it is critically loaded or critically stressed. So here I have drawn this member into 3D. Here I have marked this forces. One axial force is acting and another torque is acting. So critical point means where the stress is maximum. So we need to identify the critical point within this member. So for that, we need to find the critical section. Section is the one where the effect of load is maximum and critical point or element is the location where stress is maximum. So here we are applying two forces, two loads. One is this axial force, I can call it as F is equal to 20 kilonewton, and another one is torque. So this torque value is 1.5 kilonewton meter. This one I will be converting into SI units, which is 1500 Newton meter, and this load is 20 into 10 raised to 3 or 20,000 newtons. And the effect of this load, what this will be making, what kind of stress this will be making, and what kind of stress this will be making. All these things can be obtained from the data book. Here I will be showing you the required pages within the data books for solving this problem. So here you can see in this data book load. If the load is here, you can see this figure. In this figure, here it is subjected to a normal stress, normal load or the axial load. Corresponding equation is this one. That means normal stress will be generated and that value is force by area. And here it is bending, but in our problem it is not present. And here in this case, it is subjected to torque, and corresponding this figure 1.1t, and this equation is torsional shear stress due to this torque. This is the simplified expression, which is tau equal to T into R by J. And if it is combined, in our case, the shaft is subjected to this kind of loading. That is, this kind of loading where we are having this axial force and the torque acting. For corresponding that thing, we are having this figure 1.2. The equation can be obtained from here. Or you can, if you are knowing to evaluate the critical point and stress, then you can use this general equation for finding the principal stress that I will be explaining. Anyway, these are the page which are required for solving this problem. So here I will be explaining step by step. So due to this load, we know that the axial normal stress will be generated, and that value is equal to sigma, which is equal to force by area. So this force is given, which is 20 kilonewton, 20 into 10 raised to 3 newtons, and area is, the cross section is circular. That means here the cross section, if I am taking this cross section is circular, and its area is pi d square by 4. So I will be substituting pi by 4 into d square. This expression is, or this equation is given. Here you can see this one. This is force by area. And area diameter is 50 mm. So I will be converting it into meters, which is 0.05 square. And the unit I am getting will be of Newton per meter square or in pascals. So here I will be getting 10.18 into 10 raised to 6 Newton per meter square. 1 Newton per meter square is Pascal, and 10 raised to 6 Newton per meter square is megapascal. So this value, normal stress, is equal to 10.18 megapascal. And the next type of load acting is this torque. This is the torque, T I will be calling. And due to this, torsional shear stress will be developed. And this equation for this one, it is also given in this data book, which is this one. torque equal to T into R by J. J is the polar moment of inertia, which is pi d raised to 4 by 32. On simplifying this, you will be getting this final expression 16T by pi d cube. So I can call this as tau suffix T, torsional shear. This is equal to 16 into torque divided by pi into diameter cube. So I can give the values as 16 into torque is in Newton meters, 1500 or 1.5 kilonewton meter, pi into diameter in m meters, which is 0.05 cube. And if you are simplifying this one, you will be getting the value of torsional shear stress as 61.12 into 10 raised to 6 pascals or Newton per meter square, or this value will be getting us 61.12 megapascal. So you have evaluated the types of stresses due to these two types of load. One is axial load, which creates axial normal tensile stress, and the other one was torque, and due to that torque, torsional shear stress is developed. And we need to identify the critical point. Critical point means where this stress will be maximum, and due to this force, if you are considering these sections here, different elements, if I am dividing this into elements, then the effect of this load force will be uniformly distributed at all these points. That means it will be uniform. So all elements or points with respect to this load will be critical. So you can take any element. And if you are taking the torsion loading, for that our circular cross section is this one, and the torque applied is like this torque, and we have already obtained the torque or the torsional shears corresponding that maximum only. Here I am explaining T by J into R. So this tau will be becoming maximum when this R is maximum, and it occurs at this point. R is a variable which is measured from the center. So if you are measuring from the center, the radial variable will be maximum at this position, that is corresponding to the capital R or the diameter by 2. This is diameter by 2. And at this point, the maximum shear stress will be in this direction. The distribution, you have already studied this one. So distribution will be like this. So here, this point which is lying at the outer surface element of this shaft, this is known as critical element or critical element. And here in this one, the torque applied will be transmitted same or uniform throughout all the sections. So corresponding to load, all sections are critical, and corresponding to stresses, for the axial normal stress due to this one, all points you can take as critical point. But for the torsion loading, you can call the critical point only this one, which is lying at the outer surface element. So by combining the effect of these two load, for this problem, the critical element will be lying at any section but at this outermost point. Or that outermost point may be come here also, or here also, anywhere. That means here also, because here the effect of sigma will be same or uniform, but tau will be maximum at this outer surface only. If you are taking this point, there the effect of tau, or if you are taking this point, the radial variable is less. There the effect of shear will be minimum. Anyway, critical point is this one. And next we have to evaluate the principal stresses with these stress components sigma and tau. For that you can use this equation. That means this equation, or you can simply use this one. For that you need to draw the state of stress. First I will be drawing the state of stress. So within this element I will be marking over this critical element. So this is an element. And here due to this load, normal stress I can mark like this, sigma axial, due to the axial force applied. That same thing can be represented here also. And due to this torsional load or the torsional shear stress, the shear stress will be in this direction. Complementary shear stress will also be developed. This is known as tau T, that is tau torsional. But we are having the general equation for evaluating the principal stresses if you are knowing these stress components sigma x, sigma y and tau xy, and that is given in this equation. For evaluating the principal stresses. So here sigma x is actually, if I am drawing this element, or if I am representing it as a a rectangular element, then this will be coming like this, and here I can mark the sigma axial, and here I can mark the shear. So this will be the shear stress component, that is tau due to 2t. And if you are comparing this one, I will be taking this one and using here. So if you are comparing this one, here we are having sigma x component, which is sigma axial, tau xy component, which is our tau t, and there is no sigma y, that is there is no normal stress in this direction. So based on this similarity and by using this equation, we can find the principal stresses. So the equation for finding the principal stresses is shown in that corresponding page, or I will be writing. So sigma 1 will be our maximum principal stress and sigma 2 will be our minimum principal stress, and general equation is sigma x plus sigma y divided by 2 plus or minus. If I am substituting plus, then you will be getting the maximum, otherwise minimum. Sigma x minus sigma y by 2 the whole square plus tau xy square. This is for the general state of stress, but we are having the state of stress for our problem like this. That is, here we are having the stress component sigma x to be substituted in the above equation. Sigma x equal to sigma a, which is 10.18 megapascal, and sigma y, there is no normal stress in this state of stress, so sigma y value is 0, and tau xy is the shear in this xy plane, which is due to this torsional shear, and its value we have already obtained 61.12 megapascal. So using this one, these values you can substitute onto this one. It is, this equation is given in the previous page. Then you will be getting the maximum principal stresses, or the maximum principal stress sigma 1. This value will be equal to 66.42 megapascal, and the value of sigma 2 minimum principal stress, this will be minus 56.24 megapascal. So from this sigma 1 and sigma 2, you can evaluate the maximum shear stress, which is equal to sigma 1 minus sigma 2 divided by 2. This equation you will be getting if you are knowing the Mohr circle. Suppose if Mohr circle is of this shape, then this right extreme where it is cutting the, here we are marking the normal stress and here we are marking the shear stress. This point will be sigma 1 and this point will be sigma 2. Then this diameter of this Mohr circle is actually sigma 1 minus sigma 2, and maximum shear stress means the radius of this Mohr circle, so tau max, which is half of diameter, that is sigma 1 minus sigma 2 by 2. So if you are substituting these things, then you will be getting the value of 61.33 megapascal for this maximum shear stress. So for this problem given, that is the circular shaft of given diameter subjected to axial load and torque, that is a combined loading of torque and axial load. We have evaluated the principal stresses, that means maximum and minimum principal stress, and the maximum shear stress at the critically loaded point, and I have explained how to locate the critically loaded point. All these equations are used in this one. This is from the data book Mahadevan and Balavir Reddy, and here I explain how to obtain the critical point. That means critical location is based on the load and critical stress is based on the magnitude of stress. So hope you understood, and thanks for watching.